Okay, so section 2 gives us some basic rules and formulas to use for probability. So we have these basic rules here at the top. If an event cannot occur, then the probability is 0. If it's guaranteed to occur, its probability is 1. And that all of our probabilities should be values between 0 and 1. This is insanely important. I normally will double dock students if for some reason you do a bunch of work on a problem, like that one we saw previously, and you did male or very happy, and you forgot to subtract off that intersection and you gave me something like 1.05. This would immediately get, even if you had other supporting work that was great, I would dock you a second point for the fact that this was over 1, which is insane. So just know that that is something I will dock you as being egregious in terms of an error. And then for our entire sample space, the probability of that sample space is 1. So we have some more notation. I said those were the only 4, our and, our or, the thing by itself, and then our givens. But there is one more, and that is a complement. So not a, you can write it as a complement. You can also feel free to just type or write not a. That's completely okay. And then just as a heads up, if you're in another class or looking at other books or materials online, sometimes they'll denote this with a line above the event notation. I hate this last one because usually when we have a line above something, that's like our X bar, which is how we talk about means. So I don't love it because it's confusing to have the bar mean something in one situation and something else in a different situation. So I will always be using this, but you're welcome to use any of these 3, though I would recommend against the bar notation. So our complementary events, we can use a Venn diagram to demonstrate this. In our Venn diagram, the entire square here, which is important because a lot of students forget to draw the square portion, this denotes the entire sample space. So this entire thing, that probability of being in that sample space is 1. And then we have probability of A, which we usually denote our event A with a circle. So A complement is anything outside of that circle. So if you added A and A complement together, you should get 1. And this is sort of just a gimme. This is not a formula I'd give you. Most people, this just makes sense. So we have this question: what is the probability of rolling 2 dice that don't sum to 10? So you have 2 options here. We could go back to our sample space for rolling 2 dice and be, okay, this doesn't sum to 10, this doesn't sum to 10, this doesn't sum to 10, because we're looking for the number of things that don't sum to 10 over the total number over this 36, right? So 4, 5, but this seems like a complete and utter waste of time, especially when we already did work to see that there were only 3 ways that this thing could sum to 10. So if we know the probability of C, is what we called that event, of summing to 10 is 3 over 36, then since we're talking about not summing to 10, this is the probability of C complement or not C. And this has just got to be 1 minus 3 over 36, which will be 11 over 12, or whatever the heck that decimal is, right? So that's the easiest way, and most of the time we don't need a formula to really help us out there. It's just intuitive. The next formula, or thing we're going to talk about, is the addition rule. This will be given to you on your formula sheet, so there's no reason to waste any note card space for this. The only thing you need to know is how and when to use it. So this is the addition rule for OR. This is actually what we saw when we were talking about that happiness in marriage problem. So to find the probability of A or B, which we can use that union notation, you're going to take the probability of A, so say this is circle A, it should be labeled, it's not. Add the probability of B, in our Venn diagram, that's all of this. However, what happened is we double counted that intersection, so we're going to subtract off that middle section, which was that 221 in that previous problem. So we have our we have another example about those dice again. It says, what is the probability of rolling a double, which was our event B, or 2 dice that sum to 10, which was our event C. So we're looking for the probability of B or C. Okay, so then we can look through and we can use this notation. If we're using this notation, the only thing we want to do is we want to notice instead of A and B, we have B and C. So everywhere in this formula, I'm just going to change every A to a B and every B to a C. And this, by the way, is just a reminder, this is our AND. But again, this would be on the formula sheet, so you could easily see that. So if this is what we're looking for, we know the probability of B. We found that previously. 6 of the 36 options in terms of rolling 2 dice were double. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. We just revisited C. That was 3 out of 36. But this double counts, right? If we think about and go back to, I'll write those down again. B was 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, whereas C was 4, 6, 5, 5, and 6, 4. You can see we double counted 5, 5. It's in both categories. So that's the piece we would need to subtract off for double counting it. There is one way to roll both a double and a dice that sums to, and have the 2 dice sum to 10. So we would only have in the end 8 out of 36 ways that this could happen. And again, we could simplify, we can make that a decimal, but for this exercise, I just want us to demonstrate how this formula works. So we have our 1, 2, 3, 4, 5, 6, 7, don't double count that, 8 ways that this could happen. So then we have a definition and another rule. So if we have events that are disjoint, which is another way to say mutually exclusive, you could say either one of these, means that there's no outcomes in common. So if you were to draw their Venn diagram, the 2 circles would never intersect because there's no way for both things to happen. If that's the case, then you don't have to worry about subtracting off that extra intersection that you double counted. So if we look back to our dice rolling example, summing to 7 was our event A. 2 dice that sum to 10 was our event C. Summing to 7 and summing to 10, they can't happen, right? It's not possible to get 2 dice that sum to both 7 and to 10. And if you look at our 2 different event spaces, they have nothing in common. There's nothing in common between the A and the B event spaces. So this is going to be, if we're looking at the probability of A and B, well, there's nothing that sums to both 7 and 10, so this is 0. This is how we know that they are disjoint. Okay? They can't occur together. So if we're going to figure out the probability of 7 or 10, well, we could do all of this work by converting all the different pieces, right? But what we just, this is supposed to be C. Oops. This is just going to be 0. So we're just going to take our 6 out of 36, add it to our 3 out of 36 to get us 9 out of 36. Perfect. All right, so most of the time we won't be dealing with things like rolling dice. We'll be dealing with problems that look more like exercises 3 and 4, mostly exercise 3. So exercise 3 says, suppose 30% of kittens at a local shelter are black. So what I like to do is immediately translate any given probabilities or percents into probability notation, because a lot of times we'll be coming back to these sweet formulas and using them, and if we have things in probability notation, it makes it a lot easier to decide what formula is going to help us. So in this case, we're talking about them being black. 75% have green eyes and 24% have both. What is the probability that a kitten selected at random will have green eyes or black fur? So it looks to me like we have 2 different events, green eyes and black fur. These 30%, all it says is that they are black, so we'll make that B. Our 75% are about having green eyes, and 24% have both. So if we're thinking about B, G, both would be an and, right? And then the last thing, what we're looking for is the probability of G or B. So nothing here to say they're disjoint, right? This rule does not apply, and in fact, we know that the and isn't 0. So they are not disjoint. So it means we're going to have to use the formula from the previous page. So we're going to have to use this formula right here, right? And instead of A or B, we have G or B. So we need to replace all of the A's in that formula with G's. So probability of G plus the probability of B minus the probability of G and B. And all we're going to do is plug and chug those values. And remember, we're not going to plug the values into the parentheses because these represent these entire things. We're just going to replace them with numbers. So it looks like we have 0.81. There's an 81% chance that a kitten will have either black fur or green eyes if we randomly select it. So if you want, pause the video, try out exercise 4. Otherwise, I'll just proceed. So here, 45% have iPhones, 40% have Android, and the remaining 15% have another type of phone. We know this is not true after looking at our survey data. It was like a 95% had iPhones, but let's just pretend. So we could translate each of these. Alright, assuming a student can only have one type of phone, what does this tell us? Oops, that is not my highlighter. This is telling us right here that these are disjoint. It is only possible to have one type of phone. There is no such thing as having an iPhone and an Android. That equals 0. Alright, so what is the probability that a randomly selected student has a phone other than an iPhone? So there's two ways we can solve this. Other than an iPhone, we could solve this as probability of iPhone complement. I think this is the easiest way to solve this. If 45% have iPhones, 55% do not. The other way to solve this is to think of it other than an iPhone as an Android or an other. So this would be probability of A or O. And since they're disjoint, this is the probability of A plus the probability of O. I don't like using the abbreviated formulas. In fact, I don't give them to you on the test. So what I would do is I'd still have this. And then I would plug in, okay, A is 40%, other type of phone is 15%. What's probability someone has an Android or an other? And then I come back here and realize that, well, that's just 0. It'll be in the same thing that'll get us there. So anyways, that's the addition rule for our unions and their probabilities.